Looking at section 11.4, Introduction to Derivatives, we are going to find slopes and equations of tangent lines, find the derivative of a function, and find average and instantaneous rates of change, and find instantaneous velocity. So the first piece talks about slopes and equations of tangent lines. It tells us that the average rate of change between any 2 points on the graph of a function is the slope of the line containing the 2 points. All the way back to Algebra 1, we talked about, or when you learned it, you would have talked about a rate of change being a slope. Now, when we get into looking at curves, we can't define it as a slope as a basic regular rate of change, but they're going to have it referred to as an average rate of change, which means it's kind of an approximation, what you're noticing as you move along that curve. So it says we call this line the secant line. So a secant line is just taking between 2 points along a curve, drawing a straight line in between those 2 points, and then finding out what the slope of that line is. Now, if you remember back to Algebra 1, the slope is just the change in y compared to change in x. Or you would take your y2 minus a y1 over the x2 minus the x1, finding that change in y over change in x. So if you kind of look at what's happening on our graph, our change in our y value is going to take whatever our top piece is and subtract whatever the bottom piece is, and that's going to be represented by this piece here, the value of the function at a plus h minus the value of the function at a. And then it's going to talk about the change in our x values. Well, the change in our x values are going to go between our a and our a plus h, and so that change is going to end up being an h. We're going to look at that formula in another slide or two to kind of look more in depth at it. So secant line goes between 2 points. The next piece, as we continue on talking about getting into the tangent line, it says that the figure shows how the secant line between points P and Q changes as h approaches 0. So if you were to look from point P, the first Q that they have is they have this first line drawn in here. And then what they're going to do is they're going to say, well, what happens if I bring that point closer? Well, now I have a new line that's going between that P and that Q. And if you remember anything about slope, it's looking at the steepness of a line. So this steepness is kind of going down a little bit as you go. And then you get to the next point here, and then you're looking at the change between those 2 points. And then you have the change between those next 2 points until you eventually get to a point where you have what's called a tangent line. And if you look at this tangent line, it is just a line that goes right through only point P. There is no more point Q anymore. So it then tells us, back up to our little paragraph, it says that the limiting position of the secant line is called the tangent line to the graph of f at the point P, which is that a value and then the value of the function at a. So whatever our a value is, and that a value is going to talk about an x value, then our f of a, the value of the function evaluated at that point. So our secant lines can give us a slope of a line, and we can kind of get as close as we can to that point P where we get that tangent line, which only has the slope of that curve just at that one point. So if we were to look at the formula for this, the slope of the tangent line to the curve at a point, kind of like what we looked at 2 slides ago, it says the slope of the tangent line to the graph of a function y is equal to f of x at a, comma, f of a, is given by, now they're going to have m is your slope, and we are dealing with the tangent line, which means we're really looking just at that one point on the graph. What is the slope at that point? That's going to be our limit as h approaches 0, because if you remember, h was talking about the distance along that x value was h. So as we are getting smaller and smaller and smaller and smaller, all the way down to where that a value is, that's why we're looking at h is approaching 0, meaning that distance along that x value is a 0. But that means that in the end, we're kind of looking at dividing by 0, which is why we had to use our properties of limits. So we're going to take this formula here. We're going to have the value of the function at that a plus h. We're going to subtract the value of the function at a, and then we're dividing by that h value. So it tells us provided that this limit exists. So what we've been studying with our limits, if you are approaching 0, you can't just plug in a 0 for that h. So there's some work that we need to do to simplify down our functions. So it then says that the limit also describes the slope of the graph of f, or the function, at a comma f of a, and then it's the instantaneous rate of change of f with respect to x at a. Let's see what this looks like. So our example, finding the slope of a tangent line. So it says to find the slope of the tangent line to the graph of, we have f of x is equal to x squared minus x, and we're at the point 4, 12. So since we're at the point 4, 12, 4 is where we're looking on our graph, which means that that a value is going to be 4. If you remember, that a value was defined along that x-axis. That's that point that we're looking to find the tangent, or the slope of that tangent line. So all we need from that ordered pair is just that a is equal to 4. And then we're going to plug some values in. So all I'm going to do is wherever I see a, I'm going to plug in my 4. And so if we take our limit as h approaches 0, I'm going to take this first piece here. Maybe I'll color coordinate it a little bit for you. The value of the function at a plus h means I'm going to go to my equation, and wherever I see that x value, I'm going to plug in an a plus h. That means I'm going to have an a plus h squared minus an a plus h, except I didn't want a. Mrs. Beierschmidt's not thinking. All right, the a value we just said was going to be 4. So this needs to be a 4 plus h and then a 4 plus h here. And then from there, we are going to subtract our f of a. That means I'm going to subtract the value of my function at 4, which means I'm now going to plug in 4 for x, which means I'm just going to write this out. We're going to have a 4 squared minus 4. Some of you are smart enough to just figure that out in your head. By all means, go for it. Now I'm dividing by that last piece, which is just that h that's on the bottom. So let's clean this up a little. Let's see what we got. If we have a 4 plus h squared, that means we have a square double squared. So that means we're going to have a 16 plus 8h plus h squared. I have a minus that has to distribute out to those parentheses. So we're going to have a minus 4 and a minus h. And then if we simplify this other set of parentheses, 4 squared is 16. 16 take away 4 is going to leave us with 12. So we have a minus 12. On the bottom, we have h. Let's see what happens when we clean this up some more. Let's see. We have a 16, a minus 4, and a minus 12. Well, guess what? That's 0. I have an h squared that's left over, and like terms, I have an 8h and a minus h. So that means we're left with an h squared and a not a minus, but it will be a plus. 8h, take away 1h is going to leave us with 7h, and then we have an h on the bottom. Now, we still can't evaluate this limit as h approaches 0 because we have h alone on the bottom, so we look to see, can we factor the top, which we can. So that means if we take this down, we're still going to have our limit as h approaches 0. We can factor out an h, which leaves us with an h plus 7. Divide by h. Our h's cancel out, and so that means we are evaluating our limit as h approaches 0 of just an h plus 7, which means we have a 0 plus 7, which means our final answer is just going to end up being 7. So they're looking for the slope of the tangent line. We ended up with 7. Let's take a look at another. This one says to find the slope-intercept equation. So we're going old school. Slope-intercept equation, that means that our final answer is looking at a y is equal to mx plus b type of a final answer. The last example just wanted us to find the slope of the tangent line, which was 7. Now we're going to find the slope, but then we're going to go about writing out that final equation of that line. So find the slope-intercept equation of the tangent line to the graph of f of x is equal to the square root of x. And we're looking at that point 1, 1. Excuse me. So if I were to figure out my a value, a is going to equal 1. So we begin by finding the slope of the tangent line to the graph at 1, 1. So all I need from that ordered pair to get started with my slope is a is equal to 1. And we're going to evaluate that. So that means wherever we see that a value, we're going to plug in a 1. So that means that we're really finding the value of the function at 1 plus h minus f of 1 divided by h. So let's take and plug that in. The function that we're dealing with is a square root of whatever x is. So that means we have the value of the function at 1 plus h. That means we're going to have the square root of 1 plus h. And then we are going to subtract the value of the function at 1. So we're going to subtract the square root of 1, which some of you guys can just say the square root of 1 is 1. That's fine. And then we have this h on the bottom. So now if we were to simplify this down, let's see. I'm going to go ahead and just call this a 1 here if you guys are okay with that. I cannot evaluate that limit as h approaches 0 because I would divide by 0. That means I need to find another means to solve this. I can't factor, but I do have something that can be rationalized. We'll go ahead and rationalize the numerator. That way we can kind of get some other pieces in the denominator and see if that simplifies down better. So if we rationalize that numerator, that means we're going to need the conjugate. So we're going to multiply by the square root of 1 plus h, and then we need a plus 1. And what we do to the top, we do to the bottom. So let's see what happens here. We still have our limit as h approaches 0. Now, if we were to go ahead and multiply out that top, we end up with a 1 plus h, and then we have a minus 1. And on the bottom, I'm just going to leave this as that h times this ugly mess for now, because my hope is always that I can simplify this h from the bottom with something on the top. Now, if I look at the top, we have a positive 1 and a negative 1, which cancels. And then I also have this h on the top and this h on the bottom, which is going to cancel. So all I'm left with is a 1 divided by that square root of 1 plus h with a plus 1. And now can I evaluate as h approaches 0? I can plug in 0 for h and solve that down. So if we were to plug in that 0, we'd have 1 divided by the square root of 1 plus 0 plus 1. Which means that this is going to give us the square root of 1, which is 1. 1 plus 1 on the bottom would give us a 2 on the bottom, and we have a 1 on the top. So that means I end up with a 1/2, and that is what my slope is. My slope of the tangent line is going to be a 1/2. So now we need to go back and we need to write out that total slope-intercept form. So one last step. Once I have an ordered pair, I have 1, 1. We just said that the slope is going to end up being a 1/2. We found that the slope of the tangent line to be 1/2. So all I'm going to do is go to my point slope form, plug it in, and solve it down. So my slope is a 1/2. My x1 is going to be 1. My y1 is going to be 1. And solve that down. So y minus 1 is equal to 1/2 x minus a 1/2, and then add 1. We end up with a y is equal to 1/2 x plus 1/2. And that is the slope-intercept equation of the tangent line to that graph. So the derivative of a function, it says let y is equal to f of x denote a function f. The derivative of f at x denoted by, they have that f prime of x read as f prime of x, is defined by, we have f prime of x is equal to that same limit function that we've been dealing with. The limit as h approaches 0 of f of x plus h minus f of x. So now instead of using the a, they're just changing it up into x. I don't know why they go back and forth between x and a. They just do. So understand it's the same process. So this says provided that the limit exists, it says the derivative of function f gives the slope of f for any value of x in the domain of f prime. So just one other thing to kind of point out, derivative comes from derive. And if you derive something, that means it comes from something else. Anyway, tidbit of information. All right, so finding a derivative of a function. So find the derivative of, we have f of x is equal to x squared minus 5x, and it just says at x. And it says that is find f prime of x. So f prime of x is still going to equal the limit of or the limit as h approaches 0 of f of x plus h minus f of x divided by h. So we don't have numbers we're plugging in. We are just going to plug in some of these functions. So now we're going to take this x plus h and we are going to plug it in for x and for x. So we're going to start with an x plus h, that's squared, minus a 5 times x plus h. And then we are going to subtract our function. So we're going to subtract this whole function, x squared minus 5x. And we're going to divide that whole thing by h. So all that changes from the last example is we're not plugging in a number for that x value or that a value. We are just plugging in that x plus h. So now if I were to, let's clean up this ugly mess. We got a bunch of square double squares going on here. All right, so this beginning piece, well, not really, but x plus h squared. So square double square that out. We have an x squared plus a 2xh plus an h squared. That was that first piece. If I were to distribute out that minus 5, we'd have a minus 5x and a minus 5h. And then I need to subtract this other piece here. So we're going to subtract an x squared and minus a negative plus a 5x. And all that ugly mess is being divided by h. Let's see what cancels out. Let's see. I have a positive x squared, which is going to cancel out a minus x squared. I have a minus 5x, which is going to cancel out a positive or plus 5x. Okay, so let's see what we got left. We have a highest power, h squared. So we have an h squared, we have a plus 2xh, and we have a minus 5h, and we are dividing that by this h on the bottom. Just gotta simplify that down, right? Look at the top. They all have an h in common, so guess what I can do? I can factor out an h. If I factor out that h, I'm left with an h plus 2x minus 5 divided by h, which means that I can cancel out h and h. And so all we're left with is an h. So we're still doing the limit. So we are up to the limit as h approaches 0 of h plus 2x minus 5. And if I plug in a 0 for here, all I'm left with is a 2x minus 5. So we derived a new function. We went from one equation, we derived a new equation. That's what it means to have a derivative, deriving or coming up with a new equation. So we're going to be left with a 2x minus 5. So now what I can do is I can take that f prime of x of 2x minus 5 and I can evaluate it at two different points. We're going to evaluate it along our graph at -1 and at +3. So that means my f prime of x is that 2x minus 5. And if I were to evaluate it at -1, we'd have 2 times the -1 minus 5, which means we have a -2 minus 5, which means the slope at that point is going to end up being a -7. So the slope of the tangent line at x equals -1 is going to be a -7. And then if I plug in 3, so 2 times 3 minus 5, so 6 minus 5 gives us 1. The slope of the tangent line at x is equal to 3 is +1.